Can I help you at all with the technology here?
Sure, yeah.
Okay, get your flash drive and this one in. Awesome. I'm gonna let you drive. Find your file.
Probably just the file explorer. Should be this one, HTTP, I think. SCCUR. That's it. Alright, I might as well just get started then. Hi everybody, my name is Shrewsbury. I've been conducting plasmonic research along with my colleagues Labrato Messia and Govind Sohi, who are in the audience. We've been conducting our research along with Dr. Salakutanov and Dr. Salik at the Cal Poly Pomona Physics Department. I don't have a whole lot of time to go through everything, so I guess I should get started. First of all, an outline. I'm going to be going through the motivation for our research, the background for our research, the actual experiment itself, which is mostly computational. I'm going to be discussing the results we found, and finally I'll summarize with the conclusion. So first of all is the motivation. We started out with a goal to achieve an effective refractive index 2 times that of germanium. And germanium has the highest naturally occurring refractive index in nature of about 4.05. Our structure, the goal was to get our structure to have an effective refractive index of 8.1. So that was our original motivation. And our secondary motivation was to use Bragg gratings to couple the incident light with our structure. And I'll get more into the technicalities of that later. Now for a little bit of background. Some of what I'm going to talk about isn't on this slide, but I should probably explain what plasmonics is, because I know many of you might not know. Plasmonics is the study of the propagation of plasmons in a thin conducting material. So basically they found in the 20th century, they found that if they had a very thin metal layer on top of a very thick dielectric layer, and they had some incident electromagnetic radiation, the free electrons on the surface of the metal layer would actually start to oscillate with the same wavelength as the incident light. And that would create a propagation of what they called surface plasmon polaritons. And actually that experiment, they found short-range surface plasmon polaritons. And later on, they actually found another sort of mode of plasmons. It was long-range surface plasmon polaritons, and that is where they sandwiched the metal layer between 2 dielectrics. So sort of if you only had these first 3 layers here, that would be essentially what they did to find the long-range surface plasmon polaritons. Now what we're doing is we're taking that same structure but making it a multi-layer. So what you see here is 26 layers of alternating gold and silicon dioxide, the gold being the gold and the silicon dioxide being the gray color. And I'll get into why we chose 26 layers a little bit later. But as you can see, they're very thin layers. These are in nanometers here. So it is a very small structure. But that's necessary in order for this sort of phenomenon. And let's see. I think that's everything I wanted to say about that part. But this part is the same sort of structure, the 26 layers of alternating gold and silicon dioxide. However, it's much longer, and you can see that it's actually corrugated, and that's due to the Bragg grating. So we actually, yes. So if this was to be fabricated, we would have to actually corrugate the structure in order to couple it with the light, and I'll get into that a little bit in the next few slides. So first, our methods. As I said, most of what we've done has been computational. We are working to get this structure actually fabricated with UC Davis, but it's taking longer than expected. However, in the optimization of the structure, in order to get the effective refractive index to be 8.1, we used COMSOL multiphysics, and the analysis of the same thing with other materials was also done in COMSOL multiphysics. However, when we were actually determining the sensitivity and determining the geometry of the grading, we were using the C method developed by J. Shandazun. And now this C method is somewhat old. It was developed in the 90s, and but it still works. It's it still works. Okay, so let's actually get into the results. So first, our first goal was optimizing the number of layers in the structure. And we did this in COMSOL by setting a parametric sweep to change the number of layers at each step, and then plot the calculated effective refractive index as a function of number of layers. And as you can see here, this is only from 4 to 14 layers. It does increase quite drastically as we increase the number of layers. However, as we get to higher numbers, you can see an asymptotic relationship here. It starts to not even really affect the effective refractive index. So with this information, we were able to determine that about 26 layers was about where you start seeing no change. 20 layers would have been okay, but 26 layers is very safe. After 26 layers, there's almost no change in the effective refractive index by that variation of number of layers. And that's how we determined the 26. Now, here's the same graphs for silver, aluminum, and copper. The previous was for gold. And you can see it's the same relationship for each material. And although it's not the exact same curve, the 26 layers seems to hold for each case, as you can sort of see. So we decided that 26 layers would be a decent optimization for all four materials. And once we finished with the optimization of the number of layers, we moved on to the optimization of the thickness of the layers. And what we expected to happen is what happened. As we decreased the thickness of the layers, the effective refractive index increased. You might be wondering, why are there so many colorful lines on the graph? That's the each line corresponds to a mode propagating in the structure. So this bottom one here that doesn't really reach higher than 2 effective refractive index is the 0th order, 1st, 2nd, 3rd, 4th. So that's why there are so many lines. And the oscillations of the lines as they near thinner thicknesses is due to quantum size effects. Since the layers are so small, maybe like 10 atoms thick, you start to see quantum mechanical effects in the structure. So we are a little concerned about those effects. We believe that in actual experiments we may see slightly different results from these, but we don't think that they would change too drastically because they are very thin, but they're not thin enough to where we think that we cannot use the bulk models. And ultimately what we found from this graph is that at about a thickness of 7.5, we could achieve an effective refractive index of 8.1, which is the effective refractive index that we were trying to achieve. Yes? Oh, 5 minutes, okay. So we did the same thing for silver, aluminum, and copper, and ultimately we found that 7.5 to about 5 nanometer thickness was the optimal thickness. And now, since I'm short on time, I'll probably rush through these a little bit more. This is actually the process of determining the sensitivity with using the C method. This is the output of the C method. It gives us reflectance as a function of angle of incidence. What we give the C method is the structure of the grating, the incident wavelength of the light, and what it gives us is the reflectance as a function of angle of incidence. And this is just one curve with the cover layer of the structure being water, and then we change the refractive index of the cover layer by 10 to the negative third, and as you can see, as we changed it, the resonance angle shifted each time. Now, from there, we converted that change in resonance angle to a change in wavelength, as is the standard in the industry. And we plot with this linear relationship is about 272 nanometers per refractive index unit, which is actually very sensitive for a refractive index sensor. Now this hasn't been fabricated, it hasn't been done experimentally, but the computational results are very promising. And with a sensitivity like this, it can be used in many different applications. And now just to conclude, we were successful in creating a structure that achieved an effective refractive index of 8.1. We were successful in determining the sensitivity of that structure, and we were very happy with the result. And we believe that this sensitivity can be improved upon. The methods of improving it are analysis of the different modes. Perhaps a different mode can achieve a better sensitivity. Analysis of the confinement loss. We believe that these modes that we're analyzing might be too lossy. That we might be able to find one with less losses and maybe achieve a better sensitivity. And ultimately, our goal is perhaps protein sensing, which requires a very high sensitivity. We might be able to do other sort of sensing as well, because the results have been pretty good so far. And these are my references, Comsol Multiphysics, as we used it for most of the research, and the C method reference. And that's about it. Does anybody have any questions about it? I know somebody probably does. No? Nobody wants to ask? Yes?
I have a couple of questions. So why are we getting to this refractive index of 8.1? Why are you interested in that number, or why are you interested in doubling the refractive index of germanium?
Right. That's a good question. The reason that a lot of people doing research in refractive index sensing are so interested in getting high effective refractive indices is because that high effective refractive index can be used to achieve a high sensitivity. So if our structure had like effective refractive index of maybe 2, we would be able to couple it with a prism instead of a grating, but the sensitivity would be much not as sensitive. Basically the idea is the higher the effective refractive index of the structure, the more sensitive the sensor is. That's the general idea. Does anybody have any other questions?
I have another one.
Another one? Sure.
So you pointed out that when you studied different metals, I thought you started out with gold.
We started with gold, yes.
Gold, and then you did aluminum
And silver and copper. I did gold and silver myself. Labrado did aluminum and Gobin did copper.
Okay. So, and then with all of those metals, you said it was about 7.5 nanometer thick?
For copper, gold, and silver, it was 7.5 nanometers. For aluminum, it was 5 nanometers. Aluminum seems to be the odd one out sometimes.
So is that expected that the different metals you would get the same optimal thickness? Or
Copper was a little bit of a surprise, but silver and gold were actually, we expected it to be somewhat similar because they have a similar dielectric constants in that range. We were using a wavelength of 1550 nanometers, which is a common in telecommunications. But yeah, we were expecting silver and gold to be very similar. Copper, we expected to be in the same area, and aluminum, we expected to be a little bit different. And ultimately, it was slightly different. All right.
Thanks, Bo.
Thank you.
Great talk.
Thank you.